What's up, little boysenberry muffins? Today, we're going to talk about gravitational acceleration, and we're going to look at, it says application problems, but we're going to look at kind of a range of stuff. I took a peek through the wonderful world of AP test resources that I have available to me. And basically, I kind of looked at what they want you to learn from this sort of set of lessons. And I think we're just about at the end of our time in uniform circulation, not circulation, uniform circular motion land. And we're going to try and wrap this stuff up. So, we're going to talk about gravitational acceleration. We haven't really explicitly talked about it yet. I think you guys could figure it out on your own because, you're all pretty smart. Actually, yeah, most of you aren't very smart, but you're hardworking, and that's where it counts. You know what I mean? So we'll talk about this stuff, and then I don't know what we'll do then, but we'll look at this stuff. So let's dive into this junk. So let's start with talking about gravitational acceleration, but in the terms of the universal law of gravity. So we are looking at our universal law of gravity here. This is gravity for anything. This is gravity for you. This is gravity for that phone sitting next to you. This is gravity for planets, for space stations, for plants, for pretty much anything except stuff in the nucleus of an atom. And it might be good for that. I don't know. I don't know if they've actually measured that. You know what I mean? I feel like measuring neutrons and protons gravitating towards each other would be pretty hard just because there's so much other junk going on in there. But this is gravity for pretty much everything. So the question is, how do I get little g out of this, right? So let's talk about it. Here, gravitational everywhere. Let's just set this equal to regular weight, right? Gravity close to the surface of a planet with, nice uniform stuff. It's an approximation. So let's set it equal to weight. mg. Okay, cool. So at the end of the day, these are equal to each other. These are the same thing, right? These are how hard gravity is pulling on me, and then that's what we've colloquialized as weight. And then this is how hard gravity is pulling on me, but usually it applies to things out in space, so we don't think of it as weight, but it's weight. So let's solve for little g. Let's divide by m. Okay, so the m's cancel, and we get g. And then the m's cancel. Well, one of these m's. It's kind of hard to tell which one's which. So let's say this is us. And then this is the thing we're being attracted to, like the Earth, right? So little g is actually equal to gm over r squared. This is our acceleration due to gravity. All we did was take a force and divide it by mass. So kind of relating it back to F equals ma. If we divide the force by mass, then it turns into an acceleration, right? So little g is actually gm over r squared in disguise. Little g is three things in a trench coat pretending to be one thing in a trench coat. So if we take the gravitational constant, multiply it by the thing causing the gravitational field, and divide it by the radius of that thing, or maybe more accurately, the distance, distrance. Try again, Mr. Barton. Never mind. I give up. Never mind. Never mind. I tried twice and it wasn't going to work. This is the distance from the center of mass, which is pretty much the center of everything. It gets a little finicky when you look at like humans and things that aren't balls, but So gravitational constant times the mass of the thing divided by the distance from the center of the thing squared. that will tell us what is the acceleration due to gravity because of an object. This could be a planet, it could be a moon, it could be an asteroid or a meteor or a comet or you. It could be you, which is, I think, interesting to think about. What is your gravitational acceleration? Maybe we'll talk about that later, but not in these notes. So let's go to calculate little g for some stuff, just to make sure that it works the way we think it works. So let's find little g on Earth. What's really, really nice about this problem is that we should already know the answer to it, right? We know little g. Little g is 9.81 meters per second squared. And we round that to 10 most of the time. But we know it. So let's just use this as maybe a test case, right? To make sure we got all our math right. And we can like type into calculators and stuff. So, oh, sorry. We teleported to another problem. My bad. I didn't mean to teleport you. Secret teleport. Anyway, we do know the answer. G equals 9.81 meters per second squared. So we're going to practice plugging this in. So the mass of our Earth is this. So we're going to plug it in. G equals gm over r squared. So G, just so you don't have to look it up again, is 6.6743 times 10 to the negative 11th. The mass of our Earth is 5.972 times 10 to the 24th over our radius squared. And remember, this is in kilometers. G is in meters per second squared. So we need to turn this thing into meters. So this is going to be 6,731,000 squared. Then you type this into your calculator. Pro tip about calculators. You can type this thing as 6.6743, and then most calculators have either an E or an EE button. If you press this, it should give you an uppercase E, like this. It'll say E, and then you can just type -11. It's like a scientific notation button. That way you don't have to go through all the work of typing times 10 and then putting in an exponent and making sure it all works. Same thing here. We can do 5.972 E24. And then I would just leave this. I wouldn't go through the work of turning into scientific notation. You could. It would be 6.731 E6 squared. Type this in your calculator. I'm notoriously what's the word for mistrusting of calculators and their order of operation. They do it really well, but they do it almost too well, like suspiciously well. You know what I mean? So when I would type this in, just so I don't goof it up, I would multiply this together and then divide by this thing squared. I do it as 2 steps because, I don't know, maybe your calculators are better. Maybe this is like me being an old fogey, you know what I mean? Maybe this is like when your parents are like, don't go to bed with wet hair, it'll give you malaria, when really that's mosquitoes. You know what I mean? It might just be because when I was learning this and my calculator is like old and crusty, and it's really picky about parentheses. So, you know, to each their own. And then when you do this, your answer should be G of Earth is equal to, what I got using these exact numbers is 9.81997. So this actually rounds to 9.82, which I think is weird, because I don't think that most people would memorize it as 9.81 if it actually rounded to 2. Do you know what I mean? I think the issue is maybe like whatever search I did to find the mass of the Earth and the radius of the Earth. Maybe they're just using slightly different numbers than people at NASA use. So it's a teeny tiny bit different, but it's not a big deal. It was close enough. All right. So there we go. We got our bearings calibrated. We got our ducks straight. Now let's go test it on something we don't know. And then you could Google it. You could type G of insert planet, and then it'll spit out what the gravitational acceleration constant is for that planet. So you could go Google this at the end. I did. It works out. So let's try this one. Our moon has a mass of this. It has a radius of this. So let's use our formula. G equals GM over R squared. So this is going to be 6.6743 times 10 to the negative 11th times the mass of our moon, 7.348 times 10 to the 22nd. Notice how this is 22 and the Earth is 24. Our Earth is like 100 times more massive than the moon. That's pretty big, huh? Divided by our radius of, remember, convert kilometers to meters, 1,737,100 meters squared. How big is that compared to the Earth? The Earth is 5 million kilometers bigger. So what is that, like a little over triple? That's pretty crazy. It's big. Anyway, we plug these numbers into our calculator, and the number it should spit out is 1.622527 meters per second squared. Rounding 1.63 meters per second squared. I think usually people remember this with a 2 there, so I think the same thing is happening. The Google or Wikipedia that I'm using to get these numbers might be a little bit different than what NASA uses, but it's whatever. You're in high school. It's not that big of a difference. If you're working on something where that decimal matters, I'm sorry. I mean, I'm not going to give you money back for your satellite that just crashed into the Earth, but you know what I mean. I feel bad about it, honestly. So, okay. So there's acceleration, finding little g on any planet. You just use the universal gravitational force equation. Get rid of the little m, meaning the mass of the thing. And then this will tell you how fast stuff falls. Cool. Pretty neat. Not super like insightful or challenging, I don't think, but neat nonetheless. All right. So now let's talk about, I think I have 1, 2, 3 more questions we're going to talk about. These are just like weird random questions that have different kind of properties to them. We're going to talk about them because we're pretty much at the end of the unit. And these are some of the like weirder questions that I saw laying around the test bank. I think you know most of the information, but we'll talk about it. We'll make some force diagrams. We'll look at some graphs and stuff. It'll be fun. So, all right. So, here is a beautifully drawn diagram. Whoever made this is just mwah, you know what I mean? Chef's kiss. What a beautiful work of art. So realistic, so 3D, beautifully rendered. I love the line work. It's immaculate, honestly. But like the more I look at it, the more I think the perspective's a little funky. But we won't hold it against them, you know what I mean? Because they're trying their best out there. Just struggling for those YouTube likes, if you know what I'm saying. So, we have a cart on wheels is tied to a rotating pole on a turntable. So you got a little mass. It's tied to this pole in the middle. This whole thing is going to rotate. And it doesn't matter which way. Really not important. The turntable is motorized and has a dial to control the speed of the rotation. In the middle of the string that ties the mass to the center pole is a force gauge. That's what that little thing's supposed to be. To measure the tension of the rope. Make a qualitative graph of the tension in the rope as the speed of the turntable increases. We're going to assume frictionless, right? They didn't tell us anything about friction, so we're going to assume no friction. They didn't tell me to think about it, so I'm going to ignore it. Also, do you see how this thing's on little tiny wheels? That's so that there's no friction. So even if there was friction, it's free to roll. So the idea here is we have a mass on a rotating table. We can figure out the tension in this rope, or we can measure. We can just read it off. We can read off how fast this thing is spinning. I'm going to kind of hand wave that and just say it tells you how fast it's spinning. The number's not important. The unit's not important. And this string is going to hold us at a constant radius, so don't worry about that either. Okay. So the only thing changing here is how fast we spin, and we want to know how is that going to affect our tension in this rope. So the first thing we should do to kind of think about this problem, because it's not even really a problem, right? It doesn't give you any numbers. It's just like, what's it look like? So we'll just give it a brief description. So let's start with a force diagram here. For our block, we have the weight down. We're going to have the normal force from the turntable up. There is no friction, and this rope is going to pull along the axis of the rope. And if my turntable is on, this thing is going to fly off the edge, right? So the rope must be pulling towards the center of the pole. So we're going to put our tension this direction. Okay, so here's our force diagram. Let's maybe look at a sum of forces equation in both directions. Sum of forces in the vertical direction is the normal force minus the weight, and it's going to equal 0. Our block on wheels here isn't going to accelerate up or down. It's just going to spin around in a circle on the table. Our sum of forces in the x direction are equal to just the tension, and that equals ma because of Newton's second law. And because this is going in uniform circular motion, it's going to be spinning. We've set the velocity to some constant number here, and the radius is constant. This is uniform circular motion. So we also get to set this equal to mv squared over r. Okay. So basically what they're asking us is make a qualitative graph of the tension in the rope as the speed of the turntable increases. So the thing we're controlling is the velocity. So that's going to go on our x-axis. That's our independent variable. It's the thing we can control. And tension is going to go on our dependent axis, the vertical y-axis. Let me just make that a little more vertical looking. Okay. So we just basically want to know, what is the relationship between tension and velocity? Well, tension equals something with velocity squared. What do squared functions look like? They're parabolas, they're quadratics. So our tension is going to look like that, like a parabola. And that's really all they're asking you for here, is they want you to take a look at some equation, and you kind of have to have some intuition to know, hey, I should look at the sum of forces equation. But that's really the only kind of equations we've been looking at this whole unit. So intuition better be pretty good on that one. So we have our equation T equals mv squared over r. So if we look at the relationship between this and this, we just want to ask ourselves, what kind of graph is that function going to make? The mass is constant. We're not changing how heavy our block is. The radius is constant because our rope is the same length the whole time. So these are just constants. These, we could just turn them into like T equals C for constant v squared, and then that's our graph. Here's our x variable. So x squared times a number equals y. And y equals x squared, even with a number in front of it, is a parabola. So we should get some kind of parabola looking graph. And that's kind of the thought process you want to go through. I think you're going to have one of these on your homework. I don't necessarily know that it's much harder than that. But basically what you're going to want to do is set up an equation and just ask yourself, what's the relationship? What do graphs like that graph, like this, look like? And then you pick the best answer. Okay. Let's talk about this sweet question. Have you guys ever ridden on one of these? If you haven't, you should go find a theme park that has one. When I was a wee boy, my mother used to force me to go to church with her. But once a year, the church would have this really rad, like, carnival day. And they'd have some carnival. So it's a bunch of people who, like, do coke out of the back of a trailer. And they set up these things. And they're like... they're like real rickety and they like shake really bad and you're like, is this safe? But you know what I mean. But I apologize if your parents or loved ones set these up. I didn't mean to insinuate that they have a drug problem, but the idea is you're in this thing and it spins and you stick to the wall. But these were so tight. This was one of my favorite rides as a kid. I was too chicken to go on this thing called the Zipper, which is basically a Ferris wheel, except the Ferris wheel is like this, and then there's like hanging carts on this thing like this, and you're sitting in here. So this thing rotates in a big circle, and then these things are like a chainsaw, and they go around, and they spin like crazy. It's insane. I would never ride this. I couldn't. I never did. I was a coward. I never got on it. I didn't think it was safe. I thought people were going to die, but you know. All right. So the Gravitron, this fun looking ride here, is a well-loved amusement park ride, which spins riders inside the Gravitron and in a circle to make them literally stick to the walls. Literally, you stick to the wall like Spider-Man. It's tight. Draw a force diagram for the person riding the Gravitron. Note that the interior walls tilted outward slightly. This should maybe be apostrophe. Wall is tilted slightly. Okay, so if we look at this thing, inside of here, do you see how this is at an angle? Inside here, there's a wall. It's not quite as angled, and you're sitting in there, and you're plastered on this thing. That's you. And you are plastered to the interior wall of this thing. If you try and pick your arm up, like you stick your arm out like that, your arm feels like it's made of like concrete. It's so heavy. And then the wall inside here, I think, is on rollers, and it can slide up and down a little bit. It's pretty fun. But they're tight. You should, if you ever get a chance, go on it. I think this one's pretty safe. So we want to draw a force diagram. So looking at our person, let me draw a slightly bigger sketch of our person here. Here's our wall. Here's our person. Plastered to the wall. Yeah, like squinty eyes. Oh my gosh, all the blood, you know. So we want to know what forces are acting on this person. So let's examine. Obviously, we're going to have weight straight down. Okay, that's fair enough. Because we're at an angle here, the normal force from this wall, because if this wall weren't here, you'd be flung out the side of the Gravitron. So the wall is in our way, very similar to the way that if you're riding in a car and your friend turns too sharp, the door is in the way. So this wall is going to push outwards on you, and it always has to be perpendicular to the surface. So it's going to be that way, right? So let's draw this perpendicular. I think if we say that this is like a 30-degree angle, this will be about 30 degrees like that. That's about 30 degrees. Assuming this is 30 degrees. It might not be. We could be a little more general and just call it theta. It's not a big deal. Theta. All right. And now, for some other reasons, if we really dive into the numbers, we could hypothesize from here to the center is about 8 meters. We could guess our mass, and we could guess some coefficients and friction and stuff. But if we really dive into the numbers, this gets very, very sloppy. I initially was going to do that with you folks, and then I thought to myself, you know what? Nah. I got about halfway through the problem, and I was still doing math like down here, and I thought you wouldn't want to do that. So we're just looking at the force diagram. Okay, so here's the question, right? Is the normal force strong enough to counteract weight? So because you are on this wall, stuck here, you're not accelerating up or down. You're just spinning in a circle. So is this piece of the normal force equal to the weight? Turns out probably not. For it to be that, you would have to be spinning so stinking fast that you'd probably pass out, to be honest. So, lucky for you, there's friction between your body and this mat. So, friction would be parallel to the mat. If we weren't going in a circle and you like just threw yourself at the mat, you would slide that way. So, friction is going to push that way. So, we're going to put friction like this, and it's at a right angle to our normal force. And then this, I feel comfortable, would be our force diagram for the person in here. Yeah, pretty cool. Now, if you wanted to, you could say, well, mu equals 0.6. I have a mass of 70 kilograms. This angle is 30 degrees. And I think with those 3 pieces of information, that's enough to really bludgeon your way through this problem. And you could figure out how fast does this thing need to be spinning for you to stick to the wall. And it turns out it's not super duper fast. It's pretty fast. It's been like 30, 40 miles an hour or something like that. But it's pretty tight. So anyway, there's our force diagram. Fun little problem. Funner amusement park ride. And now let's talk about our last example. This one, I believe, will also be somewhere on your homework. Maybe not this exact problem, but I think the situation is, and I think they ask you a little bit different question. But let's examine it. I've got 3 questions for us. So let's read the setup. A small Fuego wheels car is going to attempt to drive through a loop. So this thing is going to go like that, except a little more circular. Which forces are acting on the car at the top of the loop? So when our car is right here, what are the forces acting on this car? Because, it's up there, right? It's going crazy. Why does it stick to the track? That seems unintuitive. Things fall, okay, no? So why doesn't this thing fall? Why does it go in a circle rather than falling off the track? So let's examine this, kind of talk about it, see what's interesting about it, and then we'll get you on your way. So first question is, what forces are acting on the car at the top of the loop? All right. So for our force diagram for this pink car, we obviously have weight. Always, Mr. Barton, there's always weight. Okay. So let's think about this maybe. If this thing's going really stinking fast, have you ever gone to Castles and Coasters? That's our local amusement park here in Arizona. If you're one of those poor kids watching this in like Tibet or something. But have you ever ridden the roller coaster at the theme park that has the loop? When you go around the loop, you get pressed into that seat. You feel like you're like turning into like a little old grandma or grandpa, and you're like getting real slouchy, and you feel like you're falling down into the chair. So what does the chair have to do to keep you from falling into it? The chair has to push back. So because there's a solid thing, quote unquote, under us, and we're trying to fly out of it that way, it's going to push back on us that way. So what's the force we call the force because we're touching something solid? The normal force. So let's maybe make this a little bigger. We're also going to have a normal force acting on this, and this is the force of the track pushing towards the center of the circle or perpendicular to the track itself on our car. So we have two forces. We have the normal force and the weight. Okay, so there's our force diagram. There could be friction, but because there's wheels, probably not. We'll assume probably not too much friction. So we've answered this. What forces are acting on the car at the top of the loop? We've got normal force and we have friction. Which force changes if the car drives slower? Okay, that's an interesting question, right? It seems really obvious, right? You might know the obvious answer. Does gravity pull on you less if you drive slower? Is your speed part of the weight formula? Weight equals mass times gravity times velocity? No. It doesn't depend on our speed at all. So if we go slower, our normal force is going to change. So depending on how fast we're going through this loop, that's how hard the seat is going to push on our butts. So let's perhaps examine our sum of forces, because I think this kind of begs the question, which force changes if the car drives slower? Okay, you didn't even know one of the force changes if the car drove slower. It's the normal force. Let's find out why that happens. So if we look at our sum of forces in the y direction, the vertical direction, we have negative normal force minus weight. I'm assuming down is negative and up is positive here. This equals ma, because obviously they're not going to balance. They're in the same direction. But if our car is going pretty much constant speed through this loop, and it's a circle, that's uniform circular motion, and we get mv squared over r. Cool. All right. So weight is not going to change. That's a constant, right? So our normal force, if our velocity goes down, we need less total force. Weight can't become less. You don't weigh less because you slow down. So our normal force won't push as hard. It'll gradually decrease. So the slower you go through this loop, the slower or the lower our normal force is going to become. Cool. Okay. So when would the car not make it through the loop? That's the real question, right? How slow could we go and still make it through the loop? If you go too slow, what's going to happen is you're going to roll up this. And if you're going way too slow, you'll roll like here, and then you'll roll back down. If you're going just barely not fast enough, though, you're going to, instead of following a circular path, you're going to do that. And you're going to fall off the ramp and then fall into the other side and probably hurt yourself. You could go watch a bunch of videos of Tony Hawk trying to do the loop on his skateboard. There's a bunch of times where he does this exact thing, and I think he like broke a finger or something, maybe not, but you get what I'm saying. So when would the car not make it through the loop? Okay, so to not make it through the loop, here's what would happen is you have to be going too slow. Obviously, if you're going too slow, you're not going to make it through the loop. But why? Why don't I make it through the loop? If I'm going to go through this loop, I am going to go through circular motion, and I must follow this equation. So my force has to be this big. However big it is, depending on my mass, velocity, and radius. More importantly, my mass and my radius. My velocity will determine how much force is necessary towards the center of the circle to get me to go in that loop. If I don't have enough of this force, then I don't go in the loop and I spin out like that. If I have too much of this force, I have too much force towards the center, and then my loop does this. And I get pulled towards the center more than I want, and I don't stay in a circle. I'm a like collapsing circle. So this is too fast. This is too slow. And then this is the Goldilocks zone, just right. So what happens if I go slow? Well, my normal force decreases. Okay. What happens if we get so slow that my normal force is 0? Okay, that's fine. Minus weight equals ma equals mv squared over r. But what if I slow down past the point where n is 0? Then what happens is I need less force to go in the circle, but weight doesn't change. And then what happens is I have too much force, and I'm on this center loop here. Sorry, you guys keep me on track. This should be too little force. I'm not pulling hard enough, so I spin out. This is too much force. So because I need less force because I'm going slower, but weight can't decrease, I have more weight than is necessary for this, and then I get pulled towards the center of the circle. So when would the car not make the loop? It's when you're going too slow, past the point where the normal force is 0, and weight is too strong and pulls you towards the center of the circle. Okay. So there's your notes. I hope some of these were fun. I hope they're interesting. Hopefully you learned something. I feel like sometimes when we don't calculate too much stuff, it's kind of hard to learn. It's hard to put your finger on what you learned here, right? But I think describing these things is very important for the learning process. And I think really asking yourselves, what happens if this? What happens if this other thing? What happens if this third magical thing happens? How do I get it to do this? Asking yourself questions like that is where kind of the fun of physics comes in. So hopefully we learn something by asking ourselves these questions. If you learned something, like the video. If you didn't learn something, leave a comment and tell me what you wish you had learned. But regardless, make sure you subscribe, because obviously if you learn something, you got to come back and learn more stuff. And if you didn't learn anything, then you've got to see if I took your criticism to heart from that comment you just so carefully crafted, right? You got to come back and see if I listened to your opinion. So either way, if you have questions, let me know. Otherwise, have a splendid rest of your day. I'll see you guys later.